In this video, we are going to cover the examples for our autonomous equations, in particular our autonomous first order ordinary differential equations that happen to be continuous everywhere. Our f and our partial of f with respect to x are continuous everywhere. We're going to look at systems like that, or autonomous equations of that form. So the first thing we want to do is to find our equilibrium solutions. So to do that, we can factor dx dt, or f of x up here, and find out when, or for what values of x make this thing 0. Find all of our roots of this equation. Well, if we factor this, we get x times x minus 1 times x minus 2. So in fact, our equilibrium solutions are x equals 0, 1, and 2. We're going to use that in our picture here shortly. But those are equilibrium solutions. X equals 0, x equals 1, and x equals 2. Now again, which was stated in the last video, we're going to do part 2 and 3 here at essentially the same time. And to do that, we are going to introduce the phase line. I'm going to introduce a concept called the phase line. So to do the phase line, we want to just draw this function here. So let's do that. We have x is our independent variable in this, and dx dt equal to f of x is our independent variable on this picture. We have a plane here with x comma f of x. But notice it is the derivative of x with respect to t that is the function we are graphing. So let's graph this. We can do a quick sketch by just knowing where this intersects the x-axis. So we intersect at x equals 0, at x equals 1, and at x equals 2. This is a cubic that goes through those points, and our leading term is positive, so our function looks like this. Now, what do we do? I want to draw arrows on this x-axis that tell us what our function should be doing. Well, our derivative is negative, so our function should be decreasing. In other words, x should be decreasing, right? Remember, we have the function x of t, so our function is actually x here. So along the x-axis, I'm going to point an arrow to the left to represent that x is decreasing here. And that is because the derivative is negative, right? If the derivative is negative, that means x is decreasing. On this region, our derivative is positive, so x is increasing, so I'm going to draw an arrow to the right. We're decreasing here, so an arrow to the left, and we're increasing on this region. So within each of these regions between the equilibrium solutions, I'm going to draw an arrow on that x-axis, and we will use this as our phase line. So make sure that's written down. I need to erase that now, but we are going to rotate that x-axis to be able to draw our solutions in the t comma x plane, or the tx plane. Okay. So again, this will be our phase line. We're going to take that information that I just drew down, and this was going to be our phase line. So this is going to be part 2 now. We've kind of already done part 3, but we didn't officially write the solutions out, but we'll do that after we draw the picture here in part 2. So here is our phase line, but we rotate that phase line vertically. We draw in our equilibrium solutions. X equals 0, X equals 1 here, and X equals 2. And again, with our solutions, our phase line, we had the X increasing on that region, decreasing on this region, increasing between 0 and 1, and decreasing between negative infinity and 0. Then let's draw our axis for the TX plane. And now we're going to draw in our solutions. We have an equilibrium solution at X equals 0. We have an equilibrium solution at X equals 1. And we have an equilibrium solution at X equals 2. Now what we want to do is we're going to draw in examples of our non-equilibrium solutions between each of these figures. Now, or sorry, each of these equilibrium solutions. Well, how do we do that? Well, for any initial value in the region with X less than 0, our solution is decreasing. That's what this phase line says. It says that X is decreasing on that region. All right, and that became because the dx dt, the derivative of X, was negative. So that means X is decreasing. So our solutions will look like this. And no matter what our solution is, here I've drawn more than one example of our non-equilibrium solutions on this region. The problem only asks us to do one other solution, but I drew in a couple of examples there, so you can see that no matter what the initial value is, our solutions will look like that on that region. Remember that they never intersect each other either, right? So none of these will intersect each other as long as they're different solutions. For initial values in between 0 and 1, our solution should be increasing. So in general, they will look something like this. And then they will asymptotically approach X equals 1, the equilibrium solution of X equals 1, because they can never cross. So even though it's increasing all the time and it can never cross it, that means it's going to asymptotically approach that value. Similar thing will happen between 1 and 2, except our X is decreasing. So it's going to go down and approach. The little bump should not have been in there. So let me erase that and try that again. And so it's going to asymptotically approach X equals 1, the equilibrium solution of X equals 1, if we have a non-equilibrium solution in that region. And then if we have an initial value that is placed up above X equals 2, then our solutions will look like this. And so now we've drawn out what all of our solutions should look like depending on what region they fall in on this graph. And if I erase 2 of these down here, now we actually satisfy what I asked in to be drawn in part 2 here. And we have drawn one non-equilibrium solution between all of the equilibrium solutions. And that's it. That is all for part 2. We can take each of this information and state, actually I'm going to skip ahead to part 4 since this picture is already drawn. In part 4, we want to classify each of these equilibrium solutions as either stable, unstable, or semi-stable. Well, X equals 2 is unstable. So x equals 2 is unstable because the solutions move away from that point. X equals 1 is stable, and x equals 0 is unstable. Again. All right. And then we can use this information from the phase line to write out part 3 here. And that was, if we just look at the phase line, our solution x is increasing on 0 to 1 and 2 to infinity. To be fair, our picture in part 2 also stated this or showed this. But really, we only need to think about the phase line in order to know this answer. And moreover, it was decreasing on negative infinity to 0, union 1 to 2. And that is it. We have completely solved example 1 here. We're able to draw out all types of solutions. So we know what all of our solutions will look like for this differential equation. And we know where the function is increasing or decreasing, and we know whether each equilibrium solution is either stable, unstable, or semi-stable. All right. I will stop this video there, and in our third video for this section, we will discuss example 2.